The formal charge on nitrogen?
A
Positive. And oxygen?
Negative.
Exactly.
yeah,
That's a
positive.
nitro group, so you gotta keep in mind that's what the nitro group looks like. But anyways, so yes, that's a nitration reaction. Then we have, and maybe you can help me come up with a name for this.
Oh,
We can replace one of the hydrogens with an alkyl group. What do you think that's going to be called?
Alkylation.
There you go. Alkylation reaction.
super negative, that's for substitution.
Alkylation. Right. But it has a name of the person or persons who developed this reaction attached to it, so it's called Friedel-Crafts alkylation reaction. I think we're doing acylation. Friedel-Crafts alkylation reaction. A similar reaction to alkylation is where one of the hydrogens on the benzene is replaced by an acyl group. Acyl group is this group. This is called an acyl group. Can someone tell me what's the name of this reaction? Any guesses?
Acylation.
Good. And it is also developed by the same people, so Friedel-Crafts acylation reaction. I think not this week, next week you're doing Friedel-Crafts acylation in the lab. And then finally, the fifth one is converting benzene into benzene sulfonic acid. Benzene sulfonic acid, SO3H. Once again, let's be clear. What is the structure of SO3H? What does SO3H stand for?
So
Sulf.
Double bonded oxygen and an OH single bonded.
Exactly.
okay.
This group is called a sulfonyl group. The whole
Sulf-
molecule is sulfonic acid, benzene sulfonic acid. This group is a sulfonyl group, but let me write the whole thing though. This whole molecule, if you will be called benzene sulfonic acid. So what would this reaction be called if we are introducing a sulfonyl group? What is the reaction called? Any guesses? Sulfonation. These are the 5 main types of electrophilic aromatic substitution reaction: halogenation, nitration, sulfonation, Friedel-Crafts alkylation, and Friedel-Crafts acylation. Are we all okay? Now we're going to look at each one of them one at a time. Look at the mechanisms and look at the hows and whys and all of that stuff, and then we will go from there beyond and stuff. But does anybody have a question? Okay. Now the mechanism that you will see for all 5 of them is actually the same. And the basic general mechanism that you will see for all 5 of them, which will be a pattern that you will notice, is that the benzene, by the way, will the benzene have to come as a nucleophile or electrophile?
Nucleophile.
Why? Because you're reacting it with an electrophile. Isn't that right?
Mm-hmm.
So, what you will see, some of the common things you will see in all of these individual mechanisms that we will write individually, but the common thing that you will see is that benzene will come as a nucleophile and attack the electrophile. Isn't that right?
Mm-hmm.
But now, here's the thing, you've seen this before. Pi electrons can be electron rich. I mean, we've seen alkenes reacting with electrophiles because the pi electron grabs the electrophile. Similarly, one of the pi bonds, it doesn't really matter which, but one of the pi bonds, the pi electrons attack the electrophile. If the pi electrons attack the electrophile, what does that create? Anyone?
It creates
Good. A carbocation.
carbocation.
Isn't that right? Now
Yeah.
the electrophile will go to one of the 2 carbons. It doesn't matter which. But let's say the electrophile went here. Keep in mind there are hydrogens too. I didn't write the hydrogens, but the hydrogens exist. And maybe we should write them. There are hydrogens, one hydrogen each on all the 6 carbon atoms. Isn't that right?
Yeah.
Okay, cool. So the hydrogens still exist. The hydrogens haven't lost a bit, have not been kicked out yet. They are still where they were. So, if the electrophile went to that carbon atom, what about the other carbon atom? What would the other carbon atom have? It will be positive. Do you agree?
Mm-hmm.
Now, what kind of carbocation is that? Why is it stable?
Secondary?
Okay, why is it stable?
Resonance.
It is allylic.
Oh,
Resonance. Isn't that right?
yeah.
Please take a couple of minutes. Let's write the resonance structures for this carbocation. Let's go ahead and do that. You and me together. By the way, I was noticing it in the final exam also. This is 3rd quarter Ochem, so we should not be making this mistake anymore. What is wrong? Give me a second, let me draw it first and then tell me what is wrong here.
Oh, it's not a benzene. I mean, or,
It
oh,
is not a what?
never mind.
From now on, we will lose points if this is what you're writing.
Because you didn't do the arrows.
What about the arrows?
Going both ways, it's going back and forth.
So what's wrong with this?
You're not showing how the electrons are moving, or you're showing.
Oh, okay. You're saying I didn't show the curved arrows. Okay,
Yeah.
fine. Let me do the curved arrows.
But you're not showing it reversible, you're showing it going in one direction.
Oh, you want to make it reversible? So first of all, this arrow is wrong. Absolutely, this arrow is wrong. This arrow means that this structure becomes that. That's not resonance. Resonance is not a process. Resonance is a phenomenon. Resonance is not this structure becomes that structure. Resonance is, hey, both of them don't exist. What exists is the hybrid of the two.
Mm-hmm.
You guys remember that?
Yeah.
So that's the wrong way of showing resonance. Absolutely, you will lose a point from now on.
Would it just be in the brackets?
Brackets is totally your choice, but you said reversible, Jane. So if I showed it this way, is that okay?
Yes, because it could be either one.
That's reverse. That's a process. That's an equilibrium arrow, isn't that right?
Mm-hmm. So
A
no.
and B are in equilibrium with each other. That's a dynamic process where A becomes B and B becomes A and A becomes B and so on and so forth.
Mm-hmm.
Rate of forward equals rate of reverse reaction. That's equilibrium. That's dynamic process where both A and B actually exist. So will those arrows be correct? No.
No.
Those arrows will not be correct. There is only one kind of arrow that is used to show resonance, and that is I think what you meant to say was not reversible, you meant to say a double-headed arrow.
Oh.
This is the arrow that is used to show that those structures are resonance structures of each other. And please remember, resonance structures don't actually exist. Hybrid exists. Have you guys agree? Now, as far as the brackets, you said, what about, yeah, absolutely, that's a choice. I mean, some people use it, some people don't.
Can you
So I
use
don't
that
think
instead of the arrows?
Instead of the arrows. So,
Well, if you use the.
And then could you put like a partial positive charge on all the
oh, then that's the hybrid.
Oh, okay.
Then that's the hybrid, where you are showing all the delocalization and the partial positive here and here.
So you'd
That's a
use
hybrid.
either the brackets or the arrows, or you can use
I
both.
would just do arrows.
Huh?
Let's just stick with the arrows.
Okay.
Yeah,
Is that okay?
That's.
Everybody agrees?
I agree.
Okay. Now, you did mention the hybrid, so can we draw the hybrid of the three? That was not really a question, but that's okay. What is the hybrid of the three?
Shows the delocalization of the.
So, be careful though. Where is the